I will point out one thing though. There is an error in the review document. And best thing is just to go to the bottom and show you where it is. All right. In the useful information, chapter 12, look at the bottom right-hand side. And there should be, let's see, let's see, can I edit that? That needs to be a negative. No, it's not letting me edit it yet. Edit text and images. Here we go. All right. So let me scooch over here. You can see there needs to be a negative right in front of that E sub A. Okay. Save it. Okay. To the top. We'll get started now. That looks like a minor error, but it'll make a huge difference in the answer. Here's Heather. Okay. So I picked out, as I usually do, I picked out some that I want to go over, and there are 23 of them in this selection. So that means if we've got, say 2 hours, 120, that's about 6 minutes each. So let's get a move on. Number one, if the reaction is first order, let's put the reaction up here first. We're looking at this reaction. Okay. Hydrogen peroxide plus iodide ion plus hydrogen ions. That means it's in an acidic solution. And water. All right, that's the whole equation. And it's balanced. As far as the rate goes, we only need to address concentrations of these three reactants. So let's write the rate law for this reaction. Would be some constant, and then the concentration of that one to the N power, concentration of iodide to the M power, and then the concentration of hydrogen ions to the P power. All right. We're given first order in H2O2. Okay, so we know this one's first order. We don't have to write it. If it's there, it's first order. Second order in iodide. So the order here is 2, and 0 order in hydrogen ions. Okay. So out of those selections, A through E, which one is the proper representation of this rate law? Well, this one to the 0 power is equal to 1. Right? So it goes out. It's not included. So it would be rate equals rate constant times concentration of hydrogen peroxide to the first power times the concentration of iodide to the second power. And that would be E, would be the best answer for that one. Remember when we were talking about 0 first and second order, the rate law for zero order is just rate equals K. So there it is again. By the way, what's the overall rate order of this equation, this reaction? 1 + 2 = 3. That's simple math. The overall order for this reaction is that one plus that one. And since that one's 0, it doesn't count. All right, that was number 1. Let's see, who's next? 2. Okay. A reaction has the rate law. A to the second power, B to the first power, and C, I think, to the second power. Yes. Okay. What's the question? What's the overall order? I should be able to do it now since I did one for you already. 2 + 1 + 2 is 5. Okay. So that answer is E also. And I think we showed in the lecture that the higher the rate order, the less reactant you have left after the same period of time. If you go from 0, 1, 2, then the second order reaction is going to give you the least amount of product left over. All right. Let's see, we're going to skip this one and go to number 4. If the reaction 2HI yields H2 plus I2 is second order. And so if it's second order, we're referencing only the reactant. So the rate equals K times concentration of HI to the second order. Which of the following will yield a linear plot? Okay, remember, if we're looking at the integrated rate laws, what we want to do is plot for a 0 order. Might as well put the rest of them up here. If we want to evaluate our data, which is what we're going to have to do with what we determined today in our lab, you plot time versus the concentration of, in this case, we're going to say HI. If it's 0 order, that will give you a straight line. If it's first order, then time versus the natural log of the concentration of HI. And if it's second order, it's time versus the inverse of the concentration. So that means B is the answer. Right. Four, let's go to 5. Oh, okay. Which of the following statements about enzymes is incorrect? First of all, what is an enzyme? It's a biological or a biochemical catalyst. Right? It speeds up biochemical reactions. They're usually proteins that catalyze specific biological reaction. A is correct. They are usually proteins. Not always, but usually proteins. Some are RNA. And they they catalyze specific biological reactions. They're very, very specific about the reactions they catalyze. B, they're equal to inorganic catalysts in efficiency. That's false. Enzymes are superior in efficiency. They're orders of magnitude more efficient at converting what we call a substrate into a product. So that means we found our answer. Let's see, all of these are correct. Well, no, we found an incorrect one. All right, but several thousand are known. Yes, that's true. The molecules they react with are called substrates. That's also true. So the false one is B. They are vastly superior to inorganic catalysts in their efficiency. All right, let's see. Let's scooch down to 8. A free radical is a chemical species that possesses what? Remember what a free radical is? All that you need for a free radical is at least one unpaired electron. That makes them extremely reactive. So D is the answer. And your free radical can be a compound. It can be a neutral atom. It can be an ion. It can be a polyatomic ion, as long as it has at least one unpaired electron in its electronic configuration. And there's a school of thought in human health that most of the cell damage we incur is through free radicals. Right? Chemical reactions in the body, in the cells, just naturally produce free radicals. And we have a system in place that will scavenge those free radicals and keep them from reacting where they shouldn't, especially reacting with your DNA. And certain dietary supplements are good at scavenging free radicals also. Those that have lots of double bonds in them, conjugated double bonds especially, are good at scavenging free radicals. That's why the unsaturated fatty acids are a good component of your diet. One of the reasons is that they will scavenge free radicals. All right, number 9. The rate expression for a particular reaction is A equals A and B to the second order. Okay. If the initial concentration of B is increased from 0.1 molar to what? 0.4 molar. The initial rate will increase by which of the following factors? Well, if it's going from 0.1 to 0.4, it's increasing by a factor of 4. That's 4 times in concentration for B. Well, 4 times the increase in concentration for B means 16 times for the rate. So the rate will increase by 16 times. Right? If we did that for A, it would just increase by 4 times because it's only to the first order. What if we had a 0 order in there and we increased 0.1 to 0.4? It would have 0 effect on the rate, because the rate is only proportional for 0 order components. The rate is only proportional to the K, and the K is not going to change with a change in concentration. All right, number 10. For which order reaction is the half-life of the reaction proportional to 1 over K? All right, we want to know half-life. Is it proportional to 1 over K for which of the reactions? Right? And so I don't mess up. I'm going to get useful information to be sure I write these good. All right, so for zero order, it's A0 over 2K. Over 2K. This is the half-life for zero order. The half-life for first order is 0.693 over, it's just K. Yeah. And then for second order, it's 1 over K. There we go. This is first order. This is second order. Let me check that last one to be sure. Yeah. Okay. So which one of these is proportional to 1 over K? Half-life proportional to 1 over K. You can always imagine a 1 here and a 1 here. Each one of them is proportional to 1 over K. Half-life. Half-life of each one of them is proportional to 1 over K. Now, there are other factors involved, but they're definitely proportional to the inverse of K. Each one. All right. Still right? No, good. Okay. All right, number 13. Of the following choices, which type of collision is most likely to be the rate determining step in a proposed mechanism? All right, we've got unimolecular, bimolecular, termolecular. Non-molecular is thrown in there to confuse you because of no such thing. And none of these. All right, well, that's dumb. If we have a reaction mechanism that has, let's say, unimolecular step, produces product, and we have a bimolecular step, say it produces an intermediate over here, say R, then maybe we react a component with R, that's bimolecular. Okay, and a termolecular, maybe we have another A that needs to be reacted with another B, and then we also have a C component. Right? That's termolecular. If our mechanism includes each one of these, the unimolecular, the bimolecular, and the termolecular, which one is going to be the rate determining step? The one that's least probable to happen. Right? The least probable is the one where you have to get the most reactants together at the right energy and the right orientation to produce a reaction, and that's this one. The termolecular is going to be the slowest. That's why we don't use it. It's so improbable. I mean, I say we don't use it. We avoid using this in a mechanism until we have to. If there's no other option, then we'll use a termolecular step. But they're not very common. The probability of a termolecular producing anything is very, very low. All right, so that would be C. All right, number 14. Here we go. Okay, we're going to decompose some hydrogen peroxide. This is the overall 14. The overall reaction for the decomposition of hydrogen peroxide into what they put first. They put water first. oxygen, and I think there's probably two here. Or is that just one? No, there are two. Okay, that's the overall reaction. The mechanism that's proposed is this one. And that produces H2O and an intermediate. And then the intermediate reacts with another H2O2 and produces water, oxygen, and iodine. Okay, so this is step one. And this is just proposed. I think in the lecture we showed you what the actual mechanism was. But as far as this is concerned, which of these components would be considered the catalyst? Right? What does a catalyst do? Well, it speeds up the reaction, right? But it also comes in the front door and goes out the back door and looks like it's unchanged. So here, this one comes in the front door, goes out the back door. It participates in the reaction, but it's not changed by the reaction. That's your catalyst. Now, while we're on the topic, well, how about this one? What is that one called? That's an intermediate. And it doesn't show up anywhere in this reaction. Now, where would we put the catalyst? You may not know this one. We usually put the catalyst on the arrow because it's part of the mechanism, not the overall reaction. All right. That was extra. No charge. 14. And next, let's skip a few. Let's skip a bunch. No, good. 17. Wait a minute. It's based on this information. Okay. I'm not going to write those. There are 4 experiments there. But what I will do is write the overall reaction. 2MnO4 minus, and then 5 C2H. Oops, it's backwards. H2, this must be an acid. C2O4, yep. Plus 6H plus produces product. And we don't care what the product is. Not for kinetics. All right, so we've got 4 experiments here. And they produce different rates, and they also have different concentrations, initial concentrations of each. So we're going to use the method of initial rates and determine what the order of the rate law for manganate is. So the rate law is going to look like this. Let's put it over here. Rate equals K. That's concentration of NNO4 to the N and times, I think this is oxalic acid, to the N times H plus. Okay. So what we want is to ratio 2 of these experiment results in such a way that the concentration of this one doesn't change and that one doesn't change, and we let this one change. All right, so we look at our choices, and I think experiment 1 and 2 would fit. So I'm going to put experiment 2 first in the numerator. simply because the rate is 8 times 10 to the minus 4, and the denominator then would be 2 times 10 to the minus 4. That would give us a whole number. Right? If we do it the other way, we get a fraction. And then we have to use a little math to worm our way out of that one. So the question is only referencing this one. So we only have to identify what that value is. And so the rate, let's see. The rate of experiment 2 is 8 times 10 to the minus 4. And experiment 1 is 2 times 10 to the minus 4. And these are equal to these expressions. We have a K on top, a K on the bottom, they're the same. Then we have a value for MnO4, 2 times 10 to the minus 3 to the n power, and 1 times 10 to the minus 3 to the n power. And then we have values for oxalic acid. These are both 1 times 10 to the minus 3 and 1 times 10 to the minus 3, because that's the way we selected them. And then this is 1 and 1. Okay. Now we have our a ratio set up. This one cancels that one. This one cancels that one. K's cancel. That leaves us with 2 divided into 8 is 4. And 1 divided into 2 is 2 to the n power. So n equals 2. C is the answer. Can you see that? Can you see that through my computer? All right. 17. And 18. Let's see. What's 18 referencing? That's it. It's by itself. 18. All right. The rate law for this reaction: 2 nitrogen monoxide or nitric oxide plus oxygen yields 2 nitrogen dioxide. Rate equals K times NO to the second power and O2 to the first power. What happens to the rate when the concentration of O2 is tripled? We've had one like this before, haven't we? I know we have. So NO to the second power and O2 to the first power. And we're going to triple the concentration of O2. Well, that just means the rate is tripled because it's to the first, it's the first order. What's that? Let's see. I got another diagram down here. We're going to skip that one. I think it's a duplicate. Let's see. Here we go. All right, number 24. What fraction of a reactant remains after 5 half-lives of the first reaction? So we have concentration of our reactant, and we have half-lives over here. We start out with a certain amount here, say X, and we've not gone through a half-life yet. After the first half-life, how much do we have? We have X divided by 2, don't we? 1 half-life, that by definition, it's half. If we go through a second half-life, now this one is cut in half. So that's X to the 4th, X divided by 4. And we just keep going down. Right? 8, take half of that one. Take half of this one. and take half of that. Right? So 1/32 is what we have left over after 5 half-lives. You may notice that we can also do this, right? X to the 2 to the n power equals X to the 3rd. That works too. Okay. So if I had said after 6 half-lives, be 1/64, wouldn't it? Yeah. Okay, let's see here. The following, number 25. The following question refers to 2A sub 2. Well, that's a diatomic something or other. And then this is another diatomic, yields 2 Cs. Okay. If we're given this mechanism, we take one of these plus one of those and produces one of these. Oh, plus R, left out intermediate. And then we take another one of these two plus that R, and that gives us the second C. This one is fast. This rate is fast, and this one is very slow. Okay. Went to all that trouble to ask this very simple question. Which step is the rate determining step in this mechanism? The very slow one. The slowest step in your mechanism is the rate determining step. Okay. Let's do 26. Coming up. All right. For a reaction, generic reaction makes products. A sub 0 is 6.4. All right, so if we have the concentration of A is 6.4 molar at time 0. And the first 2 half-lives are 60 and 30 minutes. So after 60 minutes, we have 3.2 molar. And after another 30 minutes, which would be a total of 90 minutes in the reaction, we'd have 1.6 molar. Right? First half-life, second half-life. If this reaction is known to be 0 order, calculate the K without units. Oh, all right. So what's the half-life expression for 0 order? Right. That's why I put it in here. So I wouldn't have to remember it either. A0 over 2K. So we've got A0 over 2K. Right, we're told it's 0 order. Okay. So since we're told it's 0 order, we don't have to worry about which one of these is which. We can use this one or we can use that one. I usually take this one and do 60 minutes. Why don't I take this one? So A sub 0 now is going to be 3.2 relative to the half-life. This is our starting position for the half-life. So this would be 3.2 molar. This would be 2 over K because K is our unknown. And the half-life now is 30 minutes. Okay, so we just need to solve for K. Let's see, bring K over here. That's 3.2 divided by 2 times 30, which would be 3.2 divided by 60. Right. I'm gonna use my calculator for this one. 5.33 times 10 to the minus 2 is K. So that would be C. Okay. I was thinking it helps to, when you have a word problem, to extract information and put it in a form that you can recognize. Those word problems are messy. On purpose. All right, let's see, who's next? Skip a few, I guess. Here we go. 31. All right. Oh, we got two temperatures and two rate constants. What does that look like? Looks like Arrhenius. Arrhenius is active here. This is the one where you're going to be using that equation that I put a correction on. Let's see, you weren't here when I gave you that. There's a correction to this formula. Natural log of K2 over K1 equals minus E sub A over R. That's the correction. In your useful information in your review document, it may be missing that minus. And this is temperature. This temperature goes to that K, and this temperature goes to this K. And this R value is 8.3145, I believe. Is that right? Yeah. Joules per mole K. That means your temperatures have to be in K, in Kelvin. All right. So if we've got a temperature of 30 degrees C plus 273 equals 303 K. And 49 degrees C plus 273 equals, let's see, 2, here's 1, 12, 322 K. What's the activation energy? Right? So let's put our values in here. The K for this one is 1.38 K1. We're going to call this T1. And this is K1. Times 10 to the minus 4. And 1.21 times 10 to the minus 3. Okay. All right, so now we can put our values in. The natural log of K2, which is 1.21 times 10 to the minus 3 over K1, which is 1.38 times 10 to the minus 4. And we're looking for activation energy. So this is our unknown. 8.3145. I'm going to leave the units out just for compactness. And 1 over T2, which is 322, minus 1 over 303K. Okay, now we want to solve for that one. Well, let's divide this one into that one and take the natural log of it. Why don't we do that first? It's 1.38. So this one is, this value right here is 8.7681. And the natural log of that, since I've already got it in my calculator, I'll just punch that button. 2.171. Okay. Then we have these values. The reciprocal of 322. Right, there's a reciprocal button in here somewhere. Okay, and then 303, reciprocal button and subtract them. So I get for this, I get minus 1.947 times 10 to the minus 4. And then what we want to do is take this negative and that value, since this is in the numerator, divide that into this value, negative, negative. So I'm going to come out with a positive value. 8.3145 divided into that, and I get 2.342 times 10 to the minus 5 E sub A. Okay. So now to get E sub A, all I have to do is divide this one into that one. And let's see. Yep. Here, positioned, I just hit divide. And I get E sub A equals 9.27 times 10 to the 4th joules. But our answer is in kilojoules. Right? All right. So how do we convert that to kilojoules? Well, you can use dimensional analysis. I mean, you can put a conversion factor out there. Or you can say, all right, what is 10 to the 4th? 10 to the 4th is 10 to the 1st times 10 to the 3rd joules. 10 to the 3rd is kilo. 1,000 is kilo. So this becomes K, and that means we have 10 to the 1st times 9.27 is 10 times that, 92.7. 92.7 kilojoules. Okay. All right. Ready. Doing pretty good. 32. Consider the following balanced reaction and the experimental results that follow. What are the rate law orders for NO and H2? All right, this one should go pretty quick. We only have 3 experiments and 2 reactants. This is the overall 2NO plus 2H2 yields, and this is irrelevant actually to doing our calculations. 2H2O. It's important for stoichiometry though. That's a gas and that's a gas. Okay, so we have for this one, our first experiment, I'm going to put the rate on this side. And so the first rate is 0.660. And the concentrations of NO be 0.015 molar, 0.020. The second rate is 1.20. Concentration of NO is 0.015 and 0.040. And the last one, 0.030. Rate, and this one's 0.020. No, excuse me, 30. And this one is 0.020. And it just dawned on me, when you're setting up, if you're actually going to do this set of experiments in the lab, how many reactants do you have? 1, 2, in this case 2. The number of experiments you need is N plus 1. If you have 2 here, you need 3 experiments. If you have 3 reactants here, you need 4 experiments to give you the right mix that will hold all concentrations constant except for one in each of the experimental pairs. So if you had 4 reactants, it would take 5 experiments to give you all the information you need. Okay, so they want what's the order of each? All right, so our rate law is going to be equal to K times concentration of NO to the N power and H2 to the N power. Right? So if we want to find the first one, we need to let nitric oxide vary in concentration, right? It won't be these two because it's the same for both. But if we take this one and this one, then that one stays the same and this one changes. So we'll take 3 and 1 for the first. And so we have 3, and here again I'm using 3. Actually, that's wrong. Yeah. We caught me at the same time. 2.40. Yeah. Okay, so this one is going to be rate 2.40 divided by the first one. Yep. 0.60 equals K and K. And now NO is going to be here, 0.030 to the N and 0.015. And then the H2 is going to stay the same at 0.020. Okay, so these two cancel, and we're left with 4, right? 4 times 0.6 is 2.4. And this is 0.015 into 0.030, which is 2 to the N. N equals 2. So this one is 2. Now, we want to let this one change and this one stay the same. So I think 2 and 1 will work here. Experiment 2 divided by experiment 1. So we have, see, that's the same. Yeah, that's the same. And this should be the same. 5, 2, 0. Okay. These values are going to change. Nope, this one's not. This one should be 5. There we go. And the rate for this one is 1.20. Okay, if I got that set up correctly. I don't have. This is 4. There we go. Okay. All right, so 0.6 into 1.2 is 2. And K's cancel. That one cancels. Then we have this one is 0.02 into 0.04 is 2 to the M. So M equals 1. Okay. So it just asks us for what's the order of NO and H2. So it's 2 and 1. C's the answer. Now, if we wanted to calculate the K, we could. Now that we know this, all we have to do is take one of these experiments, no matter which one, and put in the value for rate, then put in the value for NO, put in the value for H2, and solve for K. So if the question asks you for K, that's the next step.
When you say the value, is it the molar mass?
I'm sorry.
Like when you said to solve for K, you put in the value, is that the molar mass that you have to put in?
No, you don't have to calculate anything. This is concentration. So you just pick one of these experiments. Now that we have the orders, we just pick one of these and say, okay, concentration. Yeah, put in these values and the rate that goes with them.
Okay.
And solve for K. Yep. Whenever you see square brackets, that's concentration. $32, $33. The first order decomposition of H2O2 at minus 28 degrees C occurs with a half-life of 50 seconds. Starting with a concentration of 25.2 molar, what will be the residual concentration of H2O2 after 5 minutes? Okay, this is first order. We're given that. First order. And we're also given decomposition of H2O2 occurs with half-life of 50 seconds. And so if we have a concentration here of 2, and we have time, we have 0 time, and then 50 seconds later, we go from this to that. We're also given starting concentration 25.2. All right, so X in this case is 25.2 at the start. So half of that would be 12.7. No, 12.6. Yeah, 12.6 molar after 50 seconds. All right, we know this is first order. So what's the half-life expression for first order? Equals 0.693 over, I think is it 2K? No, it's just K. Okay. So we can calculate the K value for our expression, right? And our rate is going to be K times, actually K. No, first order, excuse me. It'll be H2O2 like that. But that doesn't have the time factor in it. Time related to concentration. What we need is the integrated rate law. So the integrated rate law for the first order is the natural log of H2O2 after a certain amount of time is minus K time plus natural log of the beginning, the initial concentration. Okay, that's the one we need because it has concentration and time related. And the question is after 5 minutes. So how much time is 5 minutes? In seconds. 300, right? 5 times 60. 300 seconds. So that's the value we want right here. Okay, we need to know K. All right, so we have 50 seconds here and 0.693 here and K there. So we just solve for K. K is going to be 0.693 divided by 50. (1.39 times 10 to the minus 2). So now we have this value minus 1.39 times 10 to the minus 2. And our time is going to be 300 seconds, after 300 seconds. And the natural log of this concentration is our beginning concentration, 25.2. And over here is our unknown. All right, so we have an equation and one unknown. Let's see, I've already got this one in my calculator. Let me change the sign and multiply by 300. All right, so this one is going to be minus 4.158 plus the natural log of 25.2. So look for LN, there it is. This is 3.2 0.227 at the negative. So this negative, that positive should give us a negative value. It's negative 0.9312. And that's the natural log of H2O2. So how do we find the value of H2O2 here? Remember your logs? Natural log is to the E. That's the base for natural logs, E. So the log of this value is the power of E. So E to the minus 0.9312 should equal concentration of H2O2. Okay. So let me punch that in as the power of E. And I get 0.39, let's see. Yep, see, 394 molar. Okay. Let's see if anybody else snuck in. Ah, there's Jasmine. All right. 33. And 34 coming up. Purpose of this insert in our review session for 19th February is that your instructor has been confused and is afraid that the students might be confused also. So let me begin by saying and we're going to use number 34 as our sample problem. But first, the Arrhenius equation that we've been using can be written two different ways. One way is this way, right, where we have K2 over K1. And let's be consistent. K2 over K1 equals the activation energy divided by the gas constant times this arrangement of temperatures. Okay. This temperature here is associated with that rate constant. This temperature is associated with that rate constant. When we put these in this order, where T1 comes before T2, T1 minus the reciprocal of T1 minus the reciprocal of T2, then there is a positive sign here. Right? When we write it this way, K2 over K1, and we reverse the order, notice we change the position, we reverse the order. Now reciprocal of T1 is subtracted from reciprocal of T2. Then we put a minus sign here. So yeah, I know what you're thinking. That's confusing. So I've checked the review documents to be sure that they're correctly written. and made comments in the video, previous comments that I'm sure you've seen by now, that depending on the way this is written, sometimes it has positive sign, sometimes negative, and it's dependent upon the order of these two. Okay, so for number 34, which reads, for this particular reaction, the rate constant has been measured to be 1.08 times 10 to the 7th at 298. All right. Let's put our data up here. So this is going to be temperature 1. Temperature 1 equals 298 K. And K1 will be 1.08 times 10 to the 7th. And T2 is going to be 233 K. And K2 is our unknown. All right. We're also given the activation energy at 11.4 kilojoules. Activation energy equals 11.4 kilojoules. And in class, I showed you that this is the same as 11,400 joules. Okay. So now to answer the question, what we need is the correct formula. We're going to use the one with a positive sign. I believe that's the way it's given in the review document, useful information. So we're going to use this one. Natural log of K2 over K1 equals E sub A over R. Excuse me. No, that's not right. Times T1 first minus T2. Okay. So now we're gonna fill in the information as given, and then solve for K2. All right. So the natural log of K2 over 1.08 times 10 to the 7th equals E sub A, which is 11,400, divided by 8.3145, and then 1 over T1, which is 298, minus 1 over T2. Oops, might as well put the value in there. 233. Okay, so if we take the reciprocal of this value minus the reciprocal of that one, multiply it times 11,400 and divide by 8.3145, we get this value, minus 1.284. Okay. And as I described in class, the log of K2 divided by this value is equal to the log of K2 minus the log of that one. Right? I expressed it this way. The log of A divided by B is equal to the log of A minus the log of B. Okay, so that's what we're going to do with this one. All right, so now we have the natural log of K2 minus the natural log of 1.08 times 10 to the 7th. Okay. This value is right here is 16.195. 195. And this is going to be a negative value. Okay. And that's equal to this value, minus 1.284. Okay. So the natural log of K2 is equal to this value plus this value. Because it's negative on this side, it'd be plus on that side. So we take this positive and subtract that negative, and that gives us a value of 14.911. Right? So put it over here. K2 then is going to be e to that power. That's the definition of logarithm. So we have K2 is equal to e to the 14.911, and then K2, excuse me, that's e. Looks like an L. This is e. So K2 then is 2.99 times 10 to the 6th. That's the rate constant at this temperature. Right? That temperature gives you this rate constant. Okay. I hope that clears things up. And I'll emphasize that before the exam next week. All right. So problem number 31 was also used the Arrhenius equation, but when I worked out that problem for you in class, it was done correctly with the correct formula. Right? There was some confusion during my presentation of number 34, so that's why I wanted to scratch that part of the video and insert this part, because this gives you the correct one from the beginning. Skip a few. There must be some repetition. Here we go. All right, we're going to need, let me shrink this down a little bit. There we go. All right. So for this diagram, 39, 40, and 41, I believe. 39, 40, and 41. These three are based upon that plot. We have potential energy here, and we have reactants up here, and we have products down here. So first thing you can tell from that is this exothermic or endothermic? You start off with energy at this level and energy at that level. It's lower energy from the reactants, so where'd the energy go? Which it's exothermic. Okay, to get this reaction started, the red line says what? The distance between this position and that position is what letter on our chart? Is E, right? That's the activation energy. No catalyst. I think that's what 39 is looking for. Which is the activation energy without a catalyst? It's E. Okay. How about which letter shows the activation energy using a catalyst? That's the blue line. It takes less energy to activate this reaction with a catalyst. So this is going to be A. Okay. And the last one, which is the activation energy for the reverse reaction without the catalyst? That means you're going this direction. So how much energy does it take to go backwards? It goes from this position up to that position. Oh, that would be C, wouldn't it? Activation energies go both directions. Right? You just define what it is. Is it going forward or is it going backwards? All right. So let's look at this one. (42). What order is this reaction with respect to SO2 CL2? I'm not going to draw that one up there. That's too much trouble. Well, if you want to know the order of the reaction with respect to SO2 CL2, SO2 CL2, you want to know that value. You plot this concentration against T, right? T versus concentration. We give you a straight line if it's zero order. Remember? If you plot T versus natural log of concentration, that gives you first order. That's what we got, natural log. Right? Look at the y-axis, natural log of SO2 CL2. This is a first order reaction. Okay. Second question is, what's the value of the rate constant, K? Well, look at the regression equation for that line is y, which is natural log of SO2 CL2, equals minus 2.20 times 10 to the minus 5 x minus 8.87 times 10 to the minus 5. So if this is first order reaction, y is natural log of SO2 CL2. This is minus K. That's K. Times time minus the natural log. Yeah. The natural log of SO2 CL2. Here. That's the y-intercept. Okay. So if negative K is this negative value, then K has to be equal to 2.20 times 10 to the minus 5. Okay. And that would be B. And so if it's a straight line with 0, it's going to be a negative slope. Straight line with first, natural logs, negative slope. If we had a second order, the straight line would be positive slope because it's the inverse. All right, that was 40. This was 43. Okay. Oh, that's it.